And so the first distribution we're going to look at is the exponential. So you should have all read this stuff already. This should be with you. Can someone define the exponential distribution? X has an exponential distribution with parameter lambda if what? So what's the definition? X is exponential with parameter lambda. If you can't answer this, this means you have not done a good job reading and preparing for class. Okay? There's two different definitions. So one definition is the density is equal to 1 over lambda e to the negative x over lambda, x greater than or equal to 0, 0 otherwise. And the other definition is it's equal to lambda e to the negative x lambda if x is greater than or equal to 0 and 0 otherwise. So these are the two different definitions for an exponential random variable. So what are the things I have to immediately check once I give you this? Yes?
It's non-negative integrates to 1.
Non-negative integrates to 1. And in fact, this is why I have the 1 over lambda here. So if I do a very simple change of variables, if I let u equal x over lambda, then du becomes dx over lambda. That's exactly what I need. In this case, I would have u equals x times lambda when I do the change of variables. So they will both integrate to 1. So I could have brought clickers, but I'm going to assume this is not a controversial question. How many of you prefer definition 1? How many of you prefer definition 2? How many of you don't get? How many of you are equal between the two? Okay. So can someone tell me? So nobody prefers definition 1. So can someone tell me why they like definition 2? Yes.
Because if lambda equals 0, you're not dealing with a situation of...
Okay, so if lambda equals 0, we don't have division by lambda, but then what's the density? 0. So
yeah, I mean, but with the one above, then it would have been like...
I would almost say that that's a point for the one above, because when lambda equals 0, this is screaming at you, don't use me. Of course. When lambda equals 0 here, what does lambda equal up here?
0.
No. Infinity. Right? Because the relationship between these two is 1 over lambda is lambda. So when lambda equals 0 down here, that's really the same as putting in a lambda equals infinity. So in both of these, 0 less than lambda less than infinity. Can we come up with another reason why we like this? I mean, this was the overwhelming favorite of the class. Yes?
Doesn't involve fractions.
Doesn't involve fractions, right? Isn't that good? Fractions bad? Okay. I will actually vote for 1. I think 1 is by far the better definition. So when you see a random variable, there are two things you should always do to it. Two questions you should ask of any random variable. After you prove it's a probability density that's non-negative, integrates to 1. What are the next things you want to know about a random variable? So what would you like to know about a random variable?
The mean.
The mean. And after you know the mean?
Moments.
The standard deviation or the variance. Right? What's the expected value? What's the average value? What is the scale of my fluctuations? Let's calculate. Mean and the standard deviation. Alright, so the expected value of x, and I'll use 1, is going to be the integral from minus infinity to infinity of x times fx of x dx. Well, if I look at my density is 0 if x is less than 0. So this is the same as integrating from 0 to infinity of x, and now multiplied by 1 over lambda e to the negative x over lambda dx. Okay, so how should I proceed with this integration? U substitution. So let's let u equal x over lambda. Could I use u equals just x? it'll just make things a little bit more of a pain later. I've got an x over lambda here, I've got an x over lambda here. Let's just let u equal x over lambda. So u equals x over lambda, du is going to be dx over lambda. The range for u is going to be the same as the range for x. So this will become a u, dx is going to become a lambda du. So I'll get the integral from 0 to infinity of lambda u e to the negative u du. Now if you want, the lambda really should be put over here. Alright, I can pull out the lambda. I have lambda integral from 0 to infinity of u e to the minus u du. How do I handle this integral? Yeah, we basically have two techniques, right? We know u substitution, we know integration by parts. If u substitution hasn't finished the job, it's time to try integration by parts. U substitution is a fancy name for it. It's really change of variables. But in the case of one dimension, change of variables, we just call it u substitution. So now we integrate by parts. What letter would you like to do when you normally do integration by parts? U.
Okay.
V and W.
F and G.
We're actually lucky here. What would you want u to be when you integrate by parts?
U.
U. So we're actually lucky. Okay, u equals u. Okay?
It says UBU.
So du is
Yes, and then dv is going to be e to the minus u du. This is a bit of an abusive notation. I hope it's not so bad. Du is du, and then v is negative e to the minus u. If you don't like this abusive notation, instead of using the letter u, what could we use?
Moo.
I'm sorry?
Moo.
Mu,
W.
w, put a tilde over it, right? So if you're uncomfortable with this, by all means, do something else. It's probably not a bad idea because you've got u here, but of course u is just u. Alright, so now we get it equals lambda, then we have uv, so negative u e to the negative u at 0 and infinity. Minus and a minus becomes a plus, integral from 0 to infinity of v du, so e to the minus u du. What's the integral of e to the minus u du from 0 to infinity? It's essentially what we just started with lambda equals 1. So I said, if you do the integration, you'll see it's a probability distribution. So we've just reduced to, this is just an exponential with parameter 1. Its integral is 1. Or just do the integration directly. Now we have to evaluate this at 0 and infinity. At 0, it's clearly 0. At infinity, we have infinity e to the negative infinity. Which wins? Infinity or e to the negative infinity? E to the negative infinity. You can do that either using L'Hopital's rule, or you could do a Taylor series expansion. So u over e to the u, you take the limit as u goes to infinity. I can use L'Hopital's rule, bless you, and then that would be the same as the limit as u goes to infinity of 1 over e to the u, which will be 0. Another approach would be u over e to the u is greater than or equal to u over u squared over 2. And the reason is if I just keep one term in the Taylor series expansion of e to the u, I've made the denominator smaller. And this is more than enough to show that this is going to... Oh, I'm sorry, I want to go the other way around. I've made the denominator smaller, so the fraction is now larger. And so that would be more than enough to show that the expression goes to 0. So when the dust settles, what do we get? We get the expected value of x is lambda, if we use method 1. Okay, so using normalization 1, we get lambda. So this is normalization 1. If we use normalization 2, what do we get? Ooh. Sorry for those who are sleeping. If we use normalization 2, what would we get? So you should be able to do it without going through all the algebra again.
1 over lambda.
1 over lambda. Great. Why 1 over lambda?
You can substitute.
Yeah, because essentially, this is playing the role of 1 over lambda. So just wherever you have a lambda, replace it with a 1 over lambda. So, if I give you an exponential random variable with parameter lambda, do you want the mean to be lambda, or do you want the mean to be 1 over lambda? I want the mean to be lambda. So this is why my vote goes to the initial normalization of 1. So one of the arguments we had against this was it has a fraction. Well, no matter what, you are stuck with a fraction somewhere. It's where do you want the fraction? Do you want the fraction in the exponential, or do you want the fraction coming in terms of the parameters of interest? I would much rather have the fraction coming in with the exponential and have the mean be lambda. If I'm talking about an exponential with parameter lambda, I want the mean to be lambda. Okay? Alright, so now what do we need to calculate next? Variance. So to save some time, I'll just, I won't save time. I'll go through the long, painful way. Alright, so we want to calculate the variance. I'll at least leave the first line. So there's a couple of ways to do the variance. Let's calculate the expected value of x squared. And we know that we have to start the integration at 0. So we have the integral from 0 to infinity of x squared 1 over lambda e to the negative x over lambda dx. So as we don't spend our entire day just integrating, let's do things a little bit faster this time. Let's let u equal what? So we're going to do 2 steps at once. What should I have u be? So I want to do a u and a dv. Let's just immediately jump to integrating by parts. What should I take for u?
X squared over 5. Or no, over lambda rather.
So we could do x squared over lambda squared. There's lots of different choices here. Let's just keep things nice and just do it as x squared. And then dv would be e to the negative x over lambda dx over lambda. And we see we really want to have the lambda there when we're integrating. That's going to make the factor come out nice. So now we would get du is 2x dx, and then v is negative e to the negative x over lambda. And that's why we needed the 1 over lambda down there with the dx. And so now we get uv at 0 infinity minus the integral from 0 to infinity of v du. Well, arguing exactly as before, we'll see the boundary term uv doesn't contribute. The minus and the minus becomes a plus, and we're left with now the integral from 0 to infinity v du. So we'll have a 2x e to the negative x over lambda dx. Okay. Is that correct? How do we evaluate this integral? Yes.
You can pull the 2 out, and then you get the same integral as before, so we know what that is.
Almost, you're off by epsilon. Is it exactly the same integral as before?
Yeah.
We're missing the lambda. So what we wanted is we wanted to have an x over lambda. So what should we pull out? 2. You were just slightly too lazy. But that's exactly what you want to do. You don't want to integrate this by parts. You want to say, hey, we know this. This was what was erased a moment ago. This is why I was saying, I could really be lazy and I don't have to erase the board that much because it's the same calculation. If I pull out a 2 lambda, I get 2 lambda integral from 0 to infinity of x 1 over lambda e to the negative x over lambda dx. This is why I can give this lecture without notes. It's really only one integration to remember. We just calculated this integral. What's this integral? Lambda. So we get 2 lambda squared. So the variance, or sigma squared, is the expected value of x squared minus the expected value of x squared. So we get sigma squared is 2 lambda squared minus lambda squared. So we get sigma squared is lambda squared, so sigma is lambda. Yep, it's very nice. Now the question is, do you buy it? Is this reasonable? So I'll write the density down here below. So fx of x was 1 over lambda e to the negative x over lambda, x greater than or equal to 0. So when the chalk settles, we got that the variance was lambda. So again, whenever I have an equation, I want to ask, is this reasonable? Do you think it's reasonable that the variance was lambda squared, the standard deviation was lambda? Do you think it's reasonable, or were you expecting that the standard deviation should be square root of lambda, or lambda squared? Do you buy that the standard deviation should be lambda and not lambda squared or square root of lambda? This is the right power of lambda. This is the most important part of the calculation. What do you think? Can you give me a reason why lambda is a good thing to get here? Yes?
Standard deviation has units, not squared. And this is
Okay. So the question is, does lambda have units? Well, if we think of x as a random variable, if we give x units of meters, then lambda is going to have the same units as x, because the mean was lambda. And notice we have the exponential of x over lambda. They cancel each other out. You can't have the exponential of a number. You can't have the exponential of a unit. You can't have the exponential of 2 meters. Because when you do your Taylor series, you get 1 plus 2 meters plus 2 meters squared over 2 factorial. You can't add lengths and areas. And in fact, if you go back a couple of hundred years, which is hard to do, but you can at least look at the old math book, they didn't like having quadratic equations with mixed signs. They only wanted to have additions on the side. So they would actually write quadratics and cubics in different ways so that you only used positive signs. And they'd have all the positives on one side equaling all the positives on the negative on the other side, and they would have special cases of how to deal with these things and not have a unified approach. Very painful. It's much better to just say, oh, let's... But when you're combining them, you have to think, well, if I have a quadratic ax squared plus bx plus c, maybe a, b, and c have different units. So I can somehow add the x squared, the x, and the constant term. So over here, when I have my exponential, I want x over lambda to be unitless. And so this is coming out perfect. Okay, any questions on the exponential? Anybody have any situations where you've seen exponential processes? For good or for ill? So where have you seen something? Yes?
So like decay.
Like decay. So if you have, radioactive decay. So francium, one of my favorites, has a half-life of 22 minutes. So every 22 minutes you lose half the francium you have. If you think of losses in France, it's not good. So anyways, so there are certain elements that decay much faster than others. Okay? Can you give me another situation where you would have an exponential process? So this is saying, the longer you wait, the less likely it is you had to wait that long.
Population.
Population. So if the population is maybe dying out.
I'm thinking of increasing.
So one thing is, you could have exponential growth. And so if you look at bacterial cultures, exponential growth is a really good model for that. But we wouldn't be drawing a random variable with exponential growth.
Well, but if you the probability that you pick, bacterium A out of the population, and the population's growing exponentially.
Good. There we go. So the probability of getting a specific bacterium that you really care about. Any science fiction fans here? So Isaac Asimov has a really good story, many, where there's a human named Ralston who is convinced that we are basically just bacteria being experimented on by aliens.
That's the one where he builds the
Yes,
facility.
that's
in
one where he
there.
builds the force shield.
Okay, yeah.
If you look at waiting times between a lot of events, a lot of times the weights are exponentially distributed. The exponential is a continuous decay. We've seen analogs that are very similar to the exponential that are just more discrete. We were flipping coins and waiting for how long until we get that first head. That's essentially a discrete version of exponential decay. I remember now, what was the Asimov story? Okay. So, there's two more distributions I want to get to today, if the battery holds out. It's new batteries. Right. So the next is the Poisson. And so the Poisson is a discrete distribution. So we say x is Poisson with parameter lambda if the probability that x equals n is lambda to the n e to the minus lambda over n factorial for n in 0, 1, 2, etc. What's the first question you should be asking?
Why is this using?
I'll accept that as the 0th question. Yes.
Is it a probability?
Is it a probability density? Does it sum to 1, and is it non-negative? The non-negative is not so bad to check if what?
Lambda is not negative.
Yeah, so we need... Alright, so now let's be really careful. What do we want to assume about lambda?
Probably positive.
What if lambda equals 0?
And the probability of 0 just makes sense. Overall,
Well, okay, so once n is at least 1, I agree that the probability will be 0. But what if n equals 0?
Undefined.
We would have 0 to the 0. What is 0 to the 0 in this case? 1. Right. In this case, 0 to the 0 would be 1. It's the only way to define 0 to the 0. Now, it seems a little silly to talk about, why would I talk about a Poisson random variable, putting probability on all the non-negative integers, if I'm only putting probability on 0? Right? That seems a little foolish to do. So here's a reason why it might not be foolish. Maybe I have some process that's converging, and then maybe over time the probabilities are changing. And then in the limit, I end up getting this spike where all the probabilities are assigned to 0. Let's ignore that. Let's be reasonable. Let's take the lambda to just be positive, okay? So the first thing is we want to check and see, is it a probability distribution? So check. And depending on how much you like algebra, this is actually fun. The sum, n goes from 0 to infinity, of lambda to the n, e to the minus lambda over n factorial. I pull out the e to the minus lambda. I have a sum, n goes from 0 to infinity, of lambda to the n over n factorial. What is the sum of lambda to the n over n factorial?
E to the lambda.
E to the lambda. So I get e to the minus lambda times e to the lambda, which is 1. So good. It does sum to 1. It is a probability distribution. Alright. I will hold off on the why we care about the Poisson random variable. Right? For now, it's just intuitively obvious that we care about this. And now, what's the next questions we ask?
What's its mean?
What's its mean? What's its variance? So when you guys arrived at Williams as freshmen, did you do like the 5-question game when you met somebody? Or what's your name? Where are you from? What are you interested in studying? Or did you just text each other? Or? I mean, how many times did you ask, people you met essentially the same set of questions when you arrived on campus?
Yeah. 3 years later, nothing's changed.
You still now? Hopefully, you're asking different people.
Different people.
Okay. So we're at least making some progress. You ask the same questions to people. Why wouldn't you do this to distributions? They don't mind, okay? So every time you see a distribution, ask it, first, of course, you make sure it's a distribution. If it's not a distribution, who cares? And just leave it alone. But then ask, what's your mean? What's your standard deviation? Later on, we'll ask if it has finite higher moments. So calculate U and sigma. Okay. So we want to calculate the expected value of x. So this is the sum, n goes from 0 to infinity, of n times lambda to the n e to the minus lambda over n factorial. Okay. So the question is, how should we approach this? Any thoughts? How could we tackle this? Any thoughts? Any methods we have? Yes?
Differentiating identity.
Good! What's the identity? You're absolutely right that we want to differentiate an identity. What's the identity?
The Taylor series, maybe?
So which one?
What we started with?
This?
No.
This?
Yeah.
Okay. So since this equals 1, let's put the e to the minus lambda on the other side. So start, e to the lambda is the sum, n goes from 0 to infinity, of of lambda to the n over n factorial. We're starting with the fact that it's a probability distribution, so it sums to 1. Now we can apply the differentiating identities. So what should we apply to both sides? What do I want to differentiate by? Lambda. Anything else?
Then multiply by lambda.
I'd multiply by lambda. Because if I multiply by lambda, when I differentiate lambda to the n, I keep it to the nth power. Well, the derivative of e to the lambda, I couldn't ask for an easier derivative, right? So I'll just get the left side is lambda, e to the lambda. What's the derivative of a sum? Sum of the derivatives. So you have to justify that. We have enough decay so that this can be formally justified. So it's the sum, n goes from 0 to infinity, of n lambda to the n over n factorial. Now what do we do? Yeah, now we just bring the e back over. Now we get lambda is the sum, n goes from 0 to infinity, of n lambda to the n e to the minus lambda over n factorial. Not bad. We got the mean. There is another way to get the mean. How else could I have gotten the mean? I mean, I love differentiating identities, so I'm happy with this proof, but there is another way. And again, most of you probably will never be using this stuff again in your lives, but the techniques are important. How do you look at something and get an idea of how to attack it? That's why I want to spend so much time on this algebra. So we've got n lambda to the n e to the minus lambda over n factorial. Just because I've given it to you this way doesn't mean that this is the right way to group things. How else could you group things? Yes?
N over n factorial.
N over n factorial, excellent, right? What's n factorial? N times n minus 1 times n minus 2. What if I somehow moved that n into here and played some games? What n would be difficult to play this game with?
0.
0. Why would 0 be bad?
Can't count -1.
So it turns out negative 1 factorial is positive infinity.
Yeah.
And later we will see 1/2 factorial is the square root of pi. Or is it 3/2 factorial?
Reasonable.
Yeah,
No, I think it's 3 halves. It's 3 halves.
Gamma
3 halves
pi.
factorial is square root of pi. So there is a way to extend the notion of factorial, and we will do that. And when you extend the notion of factorial, it turns out negative 1 factorial becomes positive infinity. So having a negative 1 factorial down below is not a problem. That said, you should be a little bit concerned about a negative 1 factorial. So why don't we just say the following? You know, when n equals 0, there's no contribution here. Why don't we just start the sum when n equals 1? And let's just do that. So this is the same as the sum, n goes from 1 to infinity, of n over n factorial, lambda to the n, e to the minus lambda. Right, it's the sum, n goes from 1 to infinity, of lambda to the n, e to the minus lambda, over n minus 1 factorial. This looks an awful lot like something we've seen before. It looks a lot like the Poisson. You know, we're starting off with n equals 1, but we have n minus 1 factorial down here, so we are having a 0, a 1, a 2, a 3. The problem is we have a lambda to the n. What should we have? Then just the n minus, so what should we pull out? Pull out a lambda. And so we get lambda, the sum, n goes from 1 to infinity, lambda to the n minus 1, e to the minus lambda over n minus 1 factorial. Or if you want to make it look friendlier, just have m goes from 0 to infinity, just change the index of summation, shift it down by 1, and you'll get lambda to the m, e to the minus lambda over n factorial. Ah, but what does that sum equal? 1. And there you go. How many people prefer differentiating identities? How many people prefer clever algebra and seeing how to group things? How many people don't care or are indifferent? Did you vote twice?
Yes.
Okay, just checking.
I voted the first time and then realized how different I was.
Okay. But you were not so indifferent that you were willing to stay with your initial vote.
No, the difference is more of a gradual realization.
Right.
You should have voted for all three then.
But that would be a lot of, I mean, that's a lot of exercise.
He wasn't indifferent to voting.
He wasn't indifferent to voting, he was just indifferent to, okay. So now, we have a choice. What's the choice? What do we have to do next? Variance. Which calculation do you want to do for variance? So this is a great opportunity to talk about algebra. Which one do you want to do? So we have two choices, right? Choose wisely. Which one do you want to do?
Well, if you're thinking of the clever algebra part,
I'm sorry?
if you think of the clever algebra part, then you think of the clever algebra.
I've already done my clever algebra part for the day. I'm exhausted, yes.
Want to differentiating identities?
I like differentiating identities, and that's going to be pretty easy. If I do that again, I'll get another n squared coming down. So the differentiating identities would be really nice. If I have an n squared over here, the algebra is going to be a little bit harder. It can be done. Okay? So I will show you how to do the algebra part. So the expected value of x squared is going to be the sum, n goes from 1 to infinity, of n squared, lambda to the n, e to the minus lambda, over n factorial. I'm going to just sketch what you would do. Okay? I would write n squared as n times what? This is not a hard question. N, right? N squared is just n times n. That's the easy part. Okay? The hard part is how do I write n? I'm sorry?
N times 1.
No. But not a bad guess. So if it's not times 1,
Plus
And
zero.
it's plus 0. Right? You've only got two choices. It's going to be plus 0. What's a good way to write n with this plus 0?
N plus minus 7.
N plus...
N minus 7. I don't know.
But then when you that's not going to combine nicely. So again, I am deliberately making the choice to sacrifice covering some material and probability to really dwell on these techniques. Okay? I really want you to get a sense of how do you attack these problems. Right? That is why I'm not trying to rush through and see how much probability can I cover. I really want you to think, how should I look at this? So I'm going to put you on the spot because you gave us the idea earlier of grouping the n with the n factorial. Why did you do that?
Because then you could cancel out the n.
Okay. So when we cancel out the n, we had a n minus 1 factorial.
If you rewrite it as n minus 1 plus 1.
Excellent. Do it like that. Why would I want to do it like that? I can now write it as n times n minus 1 plus n. Hey, we know how to handle n lambda n e to the minus lambda over n factorial. That's just the mean. That's going to just contribute what? Was that?
Like the whole thing.
I think that just contributes lambda. And now this piece over here, well, when n equals 0 or 1, it's going to be 0, so I start my sum at 2. And so when I start my sum at 2, I'll then get a sum, n goes from 2 to infinity, of lambda to the n, e to the minus lambda, over n minus 2 factorial. What do I have to pull out of the lambda to the n? I have an n minus 2 factorial down below. I pull out a lambda squared. And so I end up getting lambda squared plus lambda is the second moment. Okay? So you can do it with clever algebra. You've got to think hard about how do you want to do the clever algebra. Okay? Now if I do differentiating identities twice, I don't have to think as much. Okay? As a rule of thumb, I do like to minimize how much thinking I have to do. If I have an approach that will work, I like to use it. How many of you can factor polynomials in your head? Quadratic polynomials. So if I give you something like, x squared minus 5x plus 6. X minus 2. Okay, good. Okay, x squared minus 5x plus 1,000. Alright, so this is not something you're going to factor in your head. What would you use? Right, no thinking required. Right? Just plug in the quadratic formula and it will just generate the solution. So there are some problems where if you look at it, it's easier not to use the quadratic formula. It's easier to just steer or even visualize in your head what's the polynomial and just factor it. But if that doesn't work, you have a fallback. You can always fall back to the quadratic formula and just hack away and get the answer. It's the same thing for all of this here. Try to see if you can find a clever way to do the algebra. If you can, great. If not, you have methods you can fall back on that don't require as much thought. If I apply this operator again, I'll have an n squared. And all I have to do is take the derivative of lambda e to the lambda, and then multiply by lambda. Alright, so I have to use a product rule. I think a lot less thought is needed to use differentiation twice than it is to figure out how should I cleverly group things and write n squared as n times n minus 1 plus 1. But it's worth seeing the two and seeing how would you approach problems like this. Alright, so I'm not going to do the differentiating identities because we ended up doing the other one. It turned out it was just too much fun not to do. So we have the following. So the variance is just the expected value of x squared minus the expected value of x squared. So we get lambda squared plus lambda minus lambda squared. We get lambda. So the variance is lambda. The standard deviation is the square root of lambda. Okay? Shocking conclusion. Right? This is the opposite of what this is very different from what we had with exponential. Exponential, the mean was lambda, and the standard deviation was lambda. Now we're getting the mean is lambda, but the standard deviation is square root of lambda. Did we make an algebra mistake? Did we somehow do something wrong when we did the algebra approach? Or is this a reasonable answer? What do you think? So it all comes down to thinking, what is our variable of interest? So let me just write again the definition of Poisson. So x is Poisson with parameter lambda means the probability that it takes on the value n is lambda to the n e to the minus lambda over n factorial. What can you tell me about the units of lambda? What's true about the units of lambda? It's unitless. I have an exponential of lambda. If lambda had units, these terms would all have different values. I couldn't add them together. Also, I have lambda to the n. I can't have meters, meters squared, meters cubed, meters to the fourth. Lambda is unitless. So this is very different than the exponential being a variable. And that's why we can't just look at this and say, oh yeah, the only thing that works in terms of units is the standard deviation has to be of size lambda, maybe it's 2 lambda, maybe it's lambda over 5, something like that. We can't do that here. This is very different than the exponential. Frequently use Poisson random variables to describe the number of occurrences in a time period. They'll often do it, how many accidents do you have in an intersection? If you actually have a town with intersections. Okay? So, for something like that, how many accidents do you expect to see? There's lots of other places where the Poisson random variable comes into play. If you look at spacings between primes, we believe that that's well described by a Poisson random variable, at least in certain scales. Have I talked to you about waiting in line at a bank? Have we done that this semester? Okay. When you go to a bank, to make a deposit, not to rob it or anything, how do you manage the lines? How do the banks manage the lines? What do lines look like? Okay, you have a big snake, and you have maybe 4 tellers, and they go next. When I was young, this was a while ago, but it was more like this. Why have banks changed how they have lines?
Because the one on the left is more efficient.
Why? You'll have the same waiting time in both. The same average waiting time.
Some people won't get shafted in half a huge. I couldn't think of another word for that. Some people won't wait. Just
I'll try to give you another
enormous
word.
times.
How many of you have seen When Harry Met Sally? So when Harry Met Sally, you're introduced to the high maintenance person who takes a lot of time and has a lot of special requests and wants things done in a very particular way. So imagine you're in this situation and you have a very high maintenance person. This high maintenance person can essentially knock out this entire line. And all the people behind this high maintenance person are now having an unpleasurable experience. Over here, you can still have that high maintenance person. In both cases, this person knocks out a teller. But now what happens is, instead of having all these people get a very large wait, that wait time is now split among everybody because you have one fewer teller. So in terms of just how the line is managed, the average wait time is really the same in the two, but the extremes are much better. So now, over here, there are some people who would have had a shorter wait time in this model because they happen to be in the right line. You would much rather minimize, however, the unpleasant experience. Do you know who's really good at managing lines? Theme parks. Disneyland. These people really know how to manage lines. Supermarkets. Which model do we use in supermarkets? Why?
Because they have the things to buy inside.
Yeah, you don't want people, with big carriages, moving all over like that, going through the snake line, just it's not as easy with, shopping carriages. Most people normally don't have a shopping carriage of deposits, right? So it's really not that much of an issue with banks.
That would be the high maintenance person.
I'm sorry? Yes, they might drop something. Where else do you see snake lines like this? Airports. Your inputs are very good about. I can't answer that. So I will end the day with, I think, an interesting problem to consider. And this is a case where it's a Poisson process. So what I'm going to do is alpha is fixed, and xn is going to be n alpha mod 1, i.e. the fractional part of n alpha. So it lives in the interval 0, 1. Okay? We'll assume it's greater than 0. Alpha is greater than 0. So you just give me the fractional part. So for instance, if alpha equals square root of 2, then x1 would be approximately 0.414, x2 would be approximately 828. Okay? So here's what I can do. I can look at the set x1, x2, dot, 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 xn. And I can ask, what kind of values do I see? So these are going to be numbers between 0 and 1. And I can ask, how do these numbers fall in the interval 0, 1? Can you give me any choices of alpha where it's really easy to analyze what happens? Oh, yes, alpha equals 0. Okay, so I was expecting that, and so I made sure to take alpha to be greater than 0. But you can still be a pain and just tweak your answer ever so slightly. Instead of alpha equals 0, what should you give me? Alpha equals 1. So if alpha equals 1, then the fractional part is 0, and 2 alpha, the fractional part is 0, 3 alpha, the fractional part is 0. So if alpha is an integer, it's easy to analyze. What if alpha equals 1/2? What do I get? 0, 1/2, 0, 1/2, 0, 1/2, 0, 1/2. In fact, if alpha is a rational number with a denominator q, I'm going to get something that's periodic and it will repeat every q times. So alpha is in q implies sequence is periodic. The amazing fact is that if alpha is not in q, it implies the sequence is uniformly distributed. So what that means is if I look at the limit as n goes to infinity, the number of n less than or equal to n such that n alpha mod 1 is in AB, which is contained in 0, 1, and I divide this by n, I get b minus a. So the fraction of the time I spend in the interval AB is just b minus a. Okay? So the sequence falls uniformly. What I can do is for each n, I can sort my numbers into increasing order. Okay? For each n, sort numbers in increasing order. So sort the fractional parts into increasing order. Okay? Look at gaps between adjacent terms. So for extra credit, you can use Excel, you can use Mathematica. Do this for a couple of values of n and a couple of different values of alpha, and report to me on what you find. It is absolutely shocking what you will see. If you tweak the problem and instead let xn equal n to the k alpha, where k is greater than or equal to 2, the gaps converge to a Poisson process. They converge to Poisson. So if instead of looking at n alpha, if I look at n squared alpha, I get Poisson. For what's the probability I have gaps of a given space when I appropriately normalize? When k equals 1, you get something completely different. If you've never done this calculation before, if you do it, you should be shocked at what you get. I will not give it away, but it is shocking. Hence the shockings. Okay. Alright, so this is a good place to stop. We will continue on Friday by doing the normal distribution and then probably doing the chi-square distribution as well. So you should have read, I think, through chapter 16 by now. I'm just filling in the different stuff, going through some of the special distributions. Okay.